Okay, welcome to another module of the microcontroller courses. This is I2C, and in this communication mode, we just use two bits. The pin number 24 and number 23. Okay, and this one is SDO, and this is SDI or SDA. Okay, and what is the function of the I2C? And in this slide we can see that example we have a MCU, we call it the master, and we have the multi-slave and from one master we can transmit the data to many slaves. Just use two lines. It is SDA and SCL. And this SCL is work like the clock, and SDA, this is the data line. So that means in the I2C we can transmit and receive. Just use two lines, and we can use the multi-slave and multi-master. Okay, and because of the hardware, so please remember that if we want to use the I2C communication mode, we must have make the resistor, make the circuits like this. Resistor connect to the power, the VDD, example this is 5 volt, and connect to the line for the eliminate the noise. Okay, so in the I2C feature, we will work with something called the master and slave, and because it can transmit to multi-slave, so each slave must have the address, and the address is about 7 bit divide address. Okay, 7 bit. Okay, and we have the data line. This is SDA, and as I said before, this is a bidirectional. That means the data can transmit two ways, from master to slave and from slave to master. Okay, and the SCL, some book they will make the symbol SCLK, so but they are similar. Okay, and this is the clock to transmit the data. And this SDA and SCL line mode, they require an external pull-up resistor. Example this one, on this slide we have the microchip here, our PIC here, and we connect to the we call it one slave and one slave, right? We just use two lines like this, and this one must pull up to the VCC here. Okay, VCC here. Okay, and each slave here must define the address. And what is protocol? So to transmit, example we have because we have the master and slave, so we the first one is we want to send a byte to the slave. Okay, when to transmit the data to slave, right? So the first one is we must have something called the start bit here, and then we transmit the address. Because we have many address, so we must transmit the address that the slave we want. And the address here is very special, they just have 7 bit. they just have 7 bits. And then the last bit here is very important, very important. This will decide that we want to write or we want to read. So here, because we want to write or transmit the data, so that bit, this bit must be 0. Okay, must be 0. And after this step we will receive something called the acknowledgement from the slave. That means the slave will transmit a bit. This one is from the slave, this one is from slave. So the slave will transmit a bit to the master, and then the master transmit the data. This is the data we want, and the data here is 8 bit. Okay, the data here is 8 bit data. And after 8 bit the slave receive, and when it's finished receive, the slave will send the acknowledgement bit again. Slave will send the acknowledgement again, and then this one the master transmit the data again. And when we want to finish the protocol, we must send something called the stop bit, the stop bit here, the stop bit here. Okay, and we can see that the stop bit always high, and the start bit always low. Okay, always low. And here another, we want to read 2 bytes from the slave. That means we want to read the data from the slave. That means the slave will transmit the data to the master. So what is the master do? The master first also send the start bit, and then send the address of the slave that it want to receive the data, right? And as I said before, this and this one is just 7 bit. And as I said before, this bit is very important. Here we set 1 because we want to receive the data. So after this step, the slave with this address, will send the acknowledgement bit. That means low bit here, low bit here to the master. Okay, to the master. And then the slave here, slave will transmit the data, and then the master will send the acknowledgement, to the slave, and then the slave transmit the data again. And then if we want to finish the protocol, the master will send the stop bit. Okay, we send the stop bit.
So now let's try to understand I2C frame structure. Each I2C frame begins with a start bit and ends with a stop bit. To identify each node in a network, I2C uses device or node addressing mechanism, in which each connected node has a predefined address of 7 or 10 bits. So if network is using 7-bit addressing, total 128 devices can be connected. And for 10-bit addressing, total 1024 devices can be connected in the network. The address bits are followed by a single control bit representing whether master want to write to or read from the slave. Now if the slave exists on the network, it will respond back with an acknowledgement bit, and then master will continue in either transmit or receive mode based on the read-write bit. Now comes the data bits. After every 8 data bits in one direction, an acknowledgement bit is transmitted in other direction. So means for a write request, slave has to send back an ACK bit to the master. And in case of a read request, master has to send ACK bit after each byte received from slave. The address and data bytes are sent in most significant bit or MSB first fashion.
And these are some address, special function address associated with the I2C operations. And we can see that we have uh, the also the pure one here is for the interrupt, and here you see for the enable interrupt, right? Enable interrupt, global interrupt. Okay, and we have this one is to transmit or receive the data here. So we just read this register, we just read register, and this one is to control the mode of the I2C, and this one is the address we send to from the master, right? Master or slave, we send the address, right? So the address, and this one is the status of the data, So the first one is the SSB con register, and first one is we concentrate on first 4 bit, and this one is to control the mode for the I2C. Normally we use this mode. Okay, normally we use this mode, and from this mode we can calculate the speed or the baud rate, the speed of the transmission, So how to calculate the speed of the transmission? It's very simple. Example, we have the bit, the peak, the crystal is 12 megahertz, 12 megahertz here, and we want to generate the I2C communication with the speed is 100 kilohertz. So very easy, just use these equations. Here is 100 kilohertz, right? And this one is 12 megahertz, right? And then we can assign the C here, right? We can assign C here to the SSPAD. Okay, so when we assign the C number here, we will have the SSPAD here. Okay, so now let's discuss another bit of the SSBCON1 register. The first 3 bits we already discussed in the previous slide, and the next one is bit number 4. This is the CKB. This one is to release the control clock bit. That means, example, the bit the clock is generated like this, right? It's still not 8 bit, and we want to stop the clock. So this one is to control the clock, right? To control the clock. If we set, that means if the CKB equal to 1, that means we allow another clock. If we set it 0, we will stop the clock. Okay, that means stop the transmission. Okay, the bit number 5 is related to the serial box, so we don't use it. Bit number 6, the SSPOV. This is the receive overflow. That means we have the data in the transmission register, but we have not cleared it. So or we have not transmitted. So if we give another data, this one, if we give another data to this, to SSB pop register, this one will go to 1. Another bit is right collision bit. That means if this bit is set during the master transmit mode, it indicates that a write to the SS pop register will attempt to when I2C condition were not valid for transmission. Okay, that's okay. And another very important register of the I2C mode, this is the status of the data, this is SSB status. Okay, they have a bit, the bit 0, this is buffer full status. That means the buffer SSB pop is already have data or not. This buffer already have data or not. Okay, another is UH, that means we can update the address, and another is the bit number 2 is very important. It is the read or write. That means if this bit E1 that means the transmission is in progress, we cannot transmit anymore. Okay, we have to wait, this one go to 0. Okay, another bit is S. Okay, this one is detect. Okay, they have the start bit, they have already have the start bit, indicate a start bit is detected. Okay, and this bit number 4 is stop bit detected. Okay, stop bit detected. And another is the bit number 5 to indicate that the data we receive, this is address or the data. Okay, address or data. And another 2 bits, bit number 6 and bit number 7 in the I2C mode, we don't care about this. One. Okay, and another register to control the transmission of the I2C mode. The first is the bit 0. Okay, the bit 0. This bit 0 here. This is to star. The bit star. Okay, just set this way is equal to 1. The bit star, that means the SDA will go low. Okay, bit star. And another bit is bit number 1. Okay, to repeat the star. So repeat the star. Okay, and when we set the bit to pen E1, this one is E1, that means we set the stop condition. That means the SDA from low will go to high. Okay, and another bit is send. That means we enable the receive mode, the receive data. We want the slave want to receive data, so we have to enable this mode. Okay, and this one is another bit is bit number 4 is ACKN. This is the acknowledge vision enable bit, and this bit will relate it to the bit number 5. So bit 4 and bit 5 will go together. Okay, if we set this bit equal to 1, that means the SDA line will transmit the status bit of this one. Example, if we set this one is 0, that means when we set the bit AC can here equal to 1, it will transmit on the SDA line number 0. Or if we generate it 1, this one will generate the number 1 on the SDA line. Okay, so these 2 bits work together. Okay, and the bit number 6 is to show the master that okay, if it's equal to 1, it will know that the master does not receive any acknowledgement signal from the slave. Okay, so when we set the bit 4 and bit 5 in the slave mode, the bit 6 must be go to 0. Okay, but the bit 6 in the master. Okay, and then we have a look at the transmission flow chart. And another is bit 7. And we don't care about this one. The first two line is the signal on the SDA and SCL, and this one is what happened in the register. Okay, here when we give the start condition, that means we as I said before, we just give this one this bit equal to 1, this bit equal to 1. Okay, that means we generate a low value here, okay. When the star, when finish the star condition, this bit will become 0, automatically in the software. Okay, so that means okay, we already generate the star bit, so we can write it as the function star here. Okay, and then we transmit the data, alright, or address, right? So when we transmit, very easy, just give the data to the SS-pub register. When we give the data to SS-pub register, after the bit send will come to 0, it will transmit the data. So but remember that the if it is the address, so the address is 7 bit. Okay, that is 7 bit. And the bit number A of the data, if we set it 0, that means we want to transmit the data to the slave. If this bit equal to 1, that means we want to read the data from the slave. Okay, so normally the address will be like this. Example we send the address example A0, that means we want to transmit the data, and the address is equal to A1 here, that means we want to receive the data from the slave. Okay, and after receive the data address, the slave must transmit the acknowledged bit. So that means in the slave we just clear this bit. That means the slave already send the acknowledge. Okay. And then if we want to transmit the data or another address or another data, we just give them the data to this one. Okay, give the data to this one. Okay, and the process is similar to the previous. Okay, we just set this bit in the slave equal to 1. So okay, if we want to give the stop bit, okay, we just give the pan signal, the pan bit equal to 1. Okay. And next one is the previous we configure the master at the transmit mode, and here is we configure the transmit at the receiver. That means we receive the data from the slave. The first is we generate a star bit is similar. We give the send equal to number 1, and then it will go low automatically in the software. Okay, and then we transmit the address to the slave. Okay, and this one this is the 7 bit, and the first bit will be 1. The first bit will be 1 to tell the slave that we the master want to receive the data. And when the master receive number 1, they will give the ACK from the slave. Slave will give the ACK signal. That means in the slave they will set this bit equal to 1. Okay. Oh, sorry. We in the master we give this bit equal to 1 here. okay, is equal to 1 here, and then we read, and then the data will transmit to the master. Okay, so that means we just read the data from the buffer, and then we will give the value for the IC key data equal to 0, and then we generate this bit equal to 1. That means we will ICK from the master. Okay, ICK from the master. Okay, and if we want to receive another data, just give the bit again, and we just call this function again. Okay, just call the function again, and the procedure is similar. Okay, and after that, if we want to finish the receive, just give the pen bit equal to 1. That means we already finished the transmission. And one more important is the we generate the address for the slave, like this here. We give the address into this special function register. Okay, and then we generate some, and let's go to the number 1. We use the interrupt for the simulations. Here is the code for the example here, right? So in the code we init and then star, and then we want to transmit the data, so we give this 0 right here, right? So we transmit the number 10 and then stop, and then start again, and we want to receive, so this one is number 1, and then we receive, and then we stop here. Okay,
simulation. Before going to this tutorial, we strongly recommend you to learn the basics of I2C communication protocol. Link for I2C protocol basics tutorial is given in the description. Also, a card will come at the right side top of this video now. I2C arbitration and I2C clock structuring video is given in the suggestion as well as description. First, we shall see the code. In the code, we shall start from the main function. In the main function, firstly, I2C pins are initialized using init I2C function. Then, I2C start function sends a start bit S on I2C bus. Then, a value of 0xA0 is written on the I2C bus using I2C write byte of 0xA0 statement. After that, I2C read byte function reads a byte from the I2C bus because there is no slave attached on the I2C bus. That is why RX byte will receive a value of 0xFF. After that, an ACK-A is transmitted on I2C bus using I2C send ACK function. And this, the end of stop bit P is transmitted on I2C bus using I2C stop function. Next, we shall see the pin configuration. The code used to set different properties of I2C bus is defined here. Here, SDA pin is selected to be RC4 and SCK pin is selected to be RC3. You can't change these pins because internal I2C module in Pic16F877 uses these pins only. Also, I2C speed is defined to be 100 kbps. You can change the speed to your desired value. You can go up to a maximum of 400 kbps. Next, we shall move to init I2C function. In init I2C function, firstly, SDA and SCK pins are made inputs. And after that, different properties of I2C module are selected. For example, I2C speed is selected by writing SSPADD register and using SSPCON register. I2C is enabled in master mode. Next, we shall move to I2C start function. In I2C start function, SCN bit is set, which makes the internal I2C module to send a start bit on the I2C bus. Other functions like I2C stop are written in similar fashion. Next, we shall move to I2C write byte function. In this function, byte value is written in SSP buff register, which is then transmitted automatically by the built-in I2C module. The ACK or NAC received at the end of this byte transfer is received from the slave and returned from this function using return ACK-STAT statement. Next, we shall move to I2C read byte function. When RCEN bit is set, then 8 clock pulses are transmitted to the slave. Slave places the data on each clock pulse. This data value is saved in the SSP buff register. This register value is returned from the function in the end. Data is received in MSB first stage. Let's generate the hex file. Right click on the project and clean and build. Here we can see the build successful statement. Also, we can get the path of the generated hex file. Let's see the circuit connection. This is the circuit we are going to use in the Proteus symbol. This is the Pic16F877 I2C microcontroller. And we have the 20 MHz crystal oscillator. Then we have the I2C debugger for our debugging purpose. We have connected RC3 serial clock to I2C debugger and also SDA RC4 serial data. Let us start the Proteus simulation. Here we added the generated hex file in Proteus. Then we can start the simulation. Here we have I2C debugger. This I2C debugger tool received all the I2C messages and display them on I2C debug window. That is what we are seeing in here. Here, I2C debugger tool is telling us that first of all, it received I2C start bit yes. Then a value of 0xA0 was received. After that, there was a NAC bit named as N in the debug window. After the NAC A value of 0xFF was there on I2C bus. After that, an ACK was there, named as A in the debug window, and in the end, I2C stop bit named as P was received. Here, the I2C debugger is telling us that a pattern of S, A0, N, FF, A, P was received. But in our main function, we are sending only S, A0, FF, A, P. There is a NAC missing in the main function. The reason for this that I2C write byte function is written in such a way that it writes 8 bits of the I2C bus and then reads a single bit, that is ACK or NAC, from I2C bus. Because there is no slave attached on the I2C bus at the moment, that is why I2C write byte function reads a NAC bit. So this concludes that Pic16F877 is actually writing SA0 NFF AP pattern on the I2C bus as confirmed by this debugger tool. Also, we can expand and see each and every bit of transaction, high, low, all we can see using the I2C debugger tool. This is the end of I2C driver implementation in Pic16F877 microcontroller with Proteus simulation. This is a simple example of I2C implementation. In the next tutorial, we shall interface EEPROM through I2C with Pic16F877. Thanks for watching this video. Don't forget to subscribe this channel. Thank you.
And we go to another example. The example is to the transmission between two PIC. So one is master and one is slave. Okay, and this will read the status of block P, and then transmit the status of block B of master to the slave, and then transmit the status of block B of the slave to the block D of master. Okay, and then this is the example code here, right? So here is the transmission the data, and then this way the procedure to receive the data. Okay, and the slave address is 30. Okay, and this one is the flowchart for the slave. The slave have two modes. The first mode is just receive, and second mode, first mode is receive, and the second mode is receive and then transmit the data for the master. The first one is here. Okay, in the slave mode, when they receive the start bit, okay, when they receive the start bit, and then the data, the address data will go to the SS bub value, SS bub register. and if the first bit is 0, so that means the slave just receive the data, so here when the bit number A receive the interrupt in the slave will generate the slave will generate and the buffer full status, the buffer full register bit will go high, and then when we read the data, perform the reading the buffer, and after we read the buffer, the interrupt will go down, go low. Okay, the interrupt will go low. Okay, and the condition and then receive another data here, and then when the buffer go low, so here when receive the bit number A of the data, the buffer will go high. That's okay, already received full data. Here we don't perform the SF buffer register read, so the interrupt not go down here, not go low, so the bit buffer still high, right? You still go high, and when it's run to the bit number A here, the ACK is not valid, so they don't have any acknowledgement. So, and here we give the stop bit, and okay, we go to the mode number 2. That means we receive the address, the slave will transmit the data to the master. Okay, the first one is here is to transmit to receive the address from the master. The procedure is similar, but the difference here is the bit number A here is equal to 1. Okay, equal to 1, and after receive the acknowledgement from the master, what happened? The interrupt will go on. They will generate the interrupt here, and also the CKB. That means the clock is stop. Okay, and then we give the data for the transmission from the slave. Okay, when we give the data, the buffer will go full, to full. Okay, and when we give the data to the SS buffer, the CKB will be released, and then it start the clock again, start the clock to transmit the data here. Okay, and then when the clock start, the interrupt go down. Okay, to enable the transmission. Okay, and then the transmission of the data will go here. Okay, will go to here, and we go to here. Okay, and after we transmit all the data, the buffer full bit will go down. Okay, will go down, and when we receive or not receive the ACK value here, right? So the SS buffer will go up again. Okay, here the read write becomes 0, so that means we go to, and here is the example code from the slave example code. When the start bit, and we check the interrupt, right? We check the interrupt. If don't have any problem, right? If we have any problem here, the bit we receive will be the previous one. Okay, and here is for the receive the data. Okay, this one is the address, this one is the address receive, the address receive, and then this one is to for the it's equal to 0, right? 0 and it's equal to 1, right? So it's equal to 0, right? So both bits are 0. Okay, this bit is 0, right? And this bit is 0. What happened here? DA is 0. That means we received the address, right? The address. That means we are in the slave mode, so we receive the address. And then the read and write here. This means here, right? If it is 0, that means don't have any transmission. Okay, don't have any transmission anymore. So we receive the data. Here we receive the data. Okay, and here the difference here, right? If equal to 1, here is 1, right? So that means we will transmit the data. Okay, we transmit the data until this bit, the buffer full, will go low. Okay, will go low. Okay, and after that we set the interrupt go to 0. And if we use the CCSC compiler, it's very easy. Just concentrate on some function. First, we will declare which one is the master and which one is the slave. And then here is the start bit, right? And then we can this one is for transmit the data, right? And the stop bit. Okay, so when we want to transmit the data, we have to follow this one. Okay, for function. And in the slave, all right, if our pic is slave, so we can define like this. Okay, and then we use the reach function, right? And then here is the full or not, right? Okay, and we can use the interrupt. This is the interrupt status, interrupt symbol. Okay, and this is the example. We want to transmit the data from the master to the slave. So example 1 just transmit the data. Okay, and here this is the code for the master. Just very simple. Just if you click the button 7, so just transmit the number 5. So we declare the I2C here. Okay, and in the slave, we also declare the I2C function here. And here this is we use the interrupt for the receive. So the interrupt when we receive, so the interrupt will generate 3 times. First is, what is it? This first is the address, right? The address, and then here is the data. And we go to another more complicated case. That means the master transmit the data to the slave. The master transmit the data to the slave when you press the button 7, and then when you press the button 6, P6, you will receive the data from the slave. And the first data, the data will increase every time. And according to the program here, right? According to program, this one for the transmit and this one for the receive, right? And every time we transmit, we increase the data here, right? Increase the data. Okay. So we use the compiler for the programming. The first data will be number 5, right? Will be number 5, and then when we click another, it will increase 6, 7, 8, right? And this is the function, the program in the slave. slash big. So we define the interrupt here, right? And here this is the receive, right? We check this function. If this is true, that means we receive the data, and if this is false, that means we receive the interrupt and tell us that need to transmit the data to the master. Okay, and then the first data transmit to the master is 15, right? And this is a similar example but written using register. Okay. It is totally similar.